In this video, we'll take a look at the first part of section 24.5a, how to graph polynomial functions. So the graph of a polynomial is a smooth and continuous function, no holes, no jumps, no asymptotes. The terms increasing, decreasing, and constant are used to describe the behavior of a function over an interval as we travel left to right along the graph of the function. A function is increasing if its graph moves up as x moves to the right when the graph of f is rising. Decreasing if the graph moves down as x moves to the right when the graph of f is falling. It's constant if the graph moves horizontally as x moves to the right. So in the graph below, left to right, our function is increasing. It gets to the relative maximum at x equals 0. Then it's decreasing, a relative minimum at x equals 2. Then it's increasing, and then it's constant. So the places where it changes from increasing to decreasing, decreasing to increasing, or increasing to constant are neither increasing, decreasing, or constant. So note, this is not a graph of a polynomial. So when we talk about the intervals, we talk about the x intervals in which a function is increasing. So this function is increasing on the interval from negative infinity to 0. Notice the interval is open because it doesn't include 0. And it's also increasing on the interval from 2 to 4. So increasing here and increasing here. Then the function is decreasing on the interval from 0 to 2. Notice open interval because it's not increasing or decreasing at 0 or 2. Those are relative extrema. Then the function is constant on the interval from 4 to infinity. And again, 4 is not included in the interval. The graph of a polynomial can only change from increasing to decreasing or decreasing to increasing where the derivative is 0. So we use the derivative of a function to determine whether the function is increasing or decreasing on a given interval. So we have something called the first derivative test. If f is a differentiable function on the interval from a to b, if the derivative f prime of x is positive, greater than 0, for all x in the interval from a to b, then f is increasing. So remember, the derivative is the slope of the tangent lines. So if the tangent lines slopes are positive, then your function is increasing. If f prime of x is less than 0 or negative for all x, then f is decreasing on the interval. If f prime of x equals 0, then the first derivative rule is not decisive. It might be increasing or decreasing, or it might have a relative extreme point at that value. So a relative extrema, a relative minimum point, is a function basically that goes from decreasing to increasing. The point at which it changes is called the relative minimum. The relative minimum is the y value. The slope of a tangent line at this point, if we draw a tangent line at the minimum, the slope of the tangent line is 0. The same thing happens at a maximum point, a relative maximum. A function is going from increasing to decreasing, but the slope of a tangent line at that point is 0. But that's a relative maximum. It goes from increasing to decreasing. Relative minimum goes from decreasing to increasing. So if you have the graph of a function, you can tell from the graph the intervals on which the function is decreasing. Is the slope of the tangent line positive or negative? We can find the intervals on which the function is increasing, the slope of the tangent line positive or negative, and we can find the relative extrema. So if you're taking a look at the graph, the function is decreasing until it gets right here to x equals negative 2. Then we have a relative minimum. Then the function is increasing until we get to 0, and there's where we have a relative maximum. Decreasing again until the function gets to 1, that's a relative minimum, and then increasing again. So the function would be decreasing on the open interval from negative infinity to negative 2, and then decreasing again from 0 to 1. Notice we're not including the endpoints. And the slopes of the tangent lines would be negative. The function is increasing from negative 2 to 0, open interval, and then again from 1 to infinity. And this is where the slope of the tangent line is positive. So how do we find where a function is increasing, decreasing without having the graph? Okay, so we're going to use calculus for that. To find the relative extrema, we can get that from the graph. We have a relative minimum as the y value is about -30 at the coordinate x is equal to -2. Then there's a relative max from the graph of approximately 2 at the coordinate x equals 0, and then another relative minimum of about, it looks like it could be about -3 at x is equal to 1. From the graph, we're estimating these values, but with calculus, we can find them exactly. So a critical number is a value of x where the derivative is equal to 0. So each of these, the derivative is 0 at each of these relative max and relative min. So what we're going to do to find these critical points, the points where the derivative is 0, is take the first derivative and set it equal to 0. So all relative extrema have to occur at a critical number. If f is continuous, then the derivative can change sign only at x values where f prime of x equals 0, or at x values where f prime of x is undefined, called the critical numbers of f. So the critical numbers are the values of x where it's either undefined or your function or your derivative equals 0. So if the derivative is 0, there could be a relative max or minimum, but there doesn't have to be, so we have to check. So what we do usually is find increasing, decreasing, and relative extrema all at the same time. So how do you find intervals where a function is increasing, decreasing, and how do you know whether you have a max or a minimum? The first thing we do is find the first derivative and set it equal to 0. So we have the function y equals 12x minus x to the third. So we find the first derivative, y prime, is equal to 12 minus 3x squared. Then we take that derivative and set it equal to 0. If we add 3x squared to both sides, then divide both sides by 3, we get x squared is equal to 4. Square root both sides, we get two values. X is equal to 2 and -2. So these are critical values. Then we plot those critical numbers on a number line. So if we plot this on a number line, 0, 2 is a critical value, -2 is a critical value. So what I want to know is if I'm going to choose a test point in each interval and evaluate it in the derivative. If it's positive, then the function is increasing in that interval. If it's negative, the function is decreasing. So we use the derivative to tell whether a function is increasing or decreasing. So I'm going to select a point, f prime, on to the left of -2. Then I'm going to select a coordinate in between -2 and 2, and then select a coordinate greater than 2, an x value. And I'm going to substitute each of these into the derivative. So I get 12 minus 3 times -3 squared. So that would give me 12 minus, let's see, -3 squared is +9, 12 minus 27. So my answer is going to be negative. So that means if I picked any x value less than -2, I'd get negative. So my function is decreasing. F of 0 gives me 12 minus 3 times 0 squared, which is 12, and that's positive. That means any value between -2 and 2 in this interval is positive. That means since the slope of the tangent line is positive, my function is increasing. Then if we find f of 3, I get the same value as I did for f of -3, which is negative. So their number line, we had two critical numbers, -2 and 2. It cut the number line into 3 pieces. Pick a test point from each piece, substitute it into the derivative. If it's positive, then it's increasing. If it's negative, then it's decreasing. So to identify the intervals where the function is increasing and decreasing, then our function is increasing where the first derivative is positive. It's increasing on the interval from -2 to 2. Our function is decreasing on the interval from -infinity to -2, and again from +2 to infinity, because we ended up with a negative slopes. So to identify the critical x values, it's a relative maximum when we're going from increasing to decreasing, and a relative minimum when we're going from decreasing to increasing. So if we take a look at our graph, we're going from decreasing to increasing. So at x equals -2, since we're going from decreasing to increasing, there is a relative minimum. And then at x equals +2, there's a relative maximum because our function is going from increasing to decreasing. So how do we figure out what those values are? We take -2 and 2 and substitute them back into the original function. So the original function was 12x minus x to the third. So at x equals -2, we get y is equal to 12 times -2. Let's see, back again, 12x minus x to the third minus -2 to the third. So that gives us 12 times -2 is -24. -2 cubed is -8. Minus minus gives us a -16. So our relative minimum is -16. And at x equals 2, when we plug it in the function, we get y equals 12 times +2 minus +2 cubed, which is +24, minus 8, which is 16. So our relative maximum is 16 at the point x equals, at the x-coordinate 2. Our relative minimum is -16 at the coordinate x equals 2. So how do you check and make sure? So let's take a look at the graph and use Desmos. So if we substitute our values in there, let's see, I need to adjust the window. On the y-axis, let me go a little bit further. I'll go -20 since we found out that 16 and -16 were the max and min y values. So when you take a look at the graph, notice there's our -2, -16 is our minimum. 216 is our maximum. Our function is decreasing until we get to -2. We're increasing until we get to 2, and then decreasing again after. All right, so let's try a practice problem. We're going to find the values of x for which the functions are increasing and those of x which they are decreasing. Our practice problem is 2 plus 6x minus 3x squared. This is a parabola. So let me write it in the format you're used to. -3x squared plus 6x plus 2. So since there's a negative in front of x squared, knowing what you know about functions, we know it's going to do something like this. So we're going to get an increasing, then decreasing, and it's going to have a maximum. So the steps, find the first derivative and set it equal to 0. So the first derivative, y prime, is equal to -6x plus 6. Then we take that and set it equal to 0. Take 6x to the other side. X is equal to 1. Now if you remember, we're going to actually be finding the vertex. So remember before finding the vertex, to get your x value, it was -b over 2a. There was a little formula. Okay, calculus works with all polynomials. The -b over 2a formula only works with quadratics. Okay, so next, plot the critical number on the number line. That cuts our number line into two pieces. So we're going to choose a test point in each interval. So I'm going to let x equal 0, and then I'm going to let x equal 2, and I'm substituting it in the derivative. So y prime equals negative 6 times 0 plus 6. We end up with 6, which is positive. So that means our function is increasing. If we substitute 2 into the first derivative, I get negative 6 times 2 plus 6, which is negative 6. It's negative, so that means every value above 1 would result in a negative. So that tells us our function is decreasing. So our function is increasing on the interval from negative infinity to 1, and it's decreasing on the interval from 1 to infinity. Now, to actually find the critical relative maximum or minimum, since our function is going from increasing to decreasing, there's a relative maximum that occurs at x is equal to 1. To figure out what that maximum is, take 1 and substitute it back in the original function, which was negative 3x squared plus 6x plus 2. So when we substitute 1, we get negative 3 plus 6 plus 2, which is equal to 5. So that tells us that we have a maximum, relative maximum, of 5 occurs at the coordinate x equals 1. So just a quick sketch at the coordinate 1, 2, 3, 4, 5. There's our vertex. You know from polynomials that the y-intercept would be 2 if we put a 0 in for x. That means we have a corresponding point. And that would be the sketch of our graph.